The last part of this lecture is about paging. Now, this is the most advanced memory allocation mode, and it completely separates logical from physical memory. We are not going to discuss virtual memory today, so if it's only about paging, it's not really more complicated than segmentation. If you understood segmentation, then you will also understand paging. So make sure everything is clear about the segmentation part. When that is okay, then let's move to paging. So this is a mechanism to separate, or let's say manage disjointly physical addresses from logical ones. And it doesn't allow for, it doesn't need to allocate contiguous portions of memory for the process. The process can be completely scattered around the memory into smaller units, which are the pages. It's basically what is used in many modern operating systems. And as we will see, especially in the next lecture, it really requires cooperation between the operating system and the hardware. The idea is pretty simple. Instead of dividing a process into segments, we divide a process into pages. And a page is smaller than a segment. It's not the entire data section. It's usually a power of 2 in terms of number of addresses. We will see this. So the logical memory, it's divided into pages, and the physical memory, it's also divided into units. This one are called frames, and each frame is equal to a page. So the size of a frame is the same as the size of a page. You keep stuff on the disk organized into pages, and when you want to load a certain process into memory, a program into memory and start a process, then what you do is that you take your physical memory, which is divided into frames, and you place the pages of the process inside the frames. You don't need to put them one after the other in a contiguous fashion or order. You can just put the pages into the frames the way you want, okay? And what you need to do then is to keep track of where each page is located. So what is the frame that contains each page? In this example, we have a process. It requires 4 pages from 0 to 3. It means we need 4 frames. This is how the pages are loaded into the frames in this example. So what you do is that you maintain a page table. This is the operating system, of course. The number of rows you have in this table is equal to the number of pages you have in the process. Each row refers to a page, and the content is the frame where you can find that page. So page 0 is row 0, and it's frame 1. So if you go in frame 1, you have page 0. Page 1 is row 1, or the second row, and it's frame 4. You go inside frame 4, and you have page 1, and so on, okay? Now, when the CPU needs to read or write something from the memory, the idea is similar to what we had before with segmentation. This is why I'm saying that it's not completely different from segmentation. You need to specify the page you want to access, and then within the page, the offset, okay? What is nice, though, is that this specifying the page and inside the page, the address, can be done very efficiently in a single operation. So the time complexity is 01, just by translating in a certain way the logical address of the process into page and offset. Okay, so how does the CPU know which page it should access? We said before the process thinks that it has a range of addresses that go from 0 to a certain limit. So when it says I want to access address 100, how do we compute in which page and what is the offset of address 100 if we are using pages? Well, this is how you do it. So I'm going a bit rapidly here, but then check the slides and try it out yourself. If the size of the page or the frame, they have the same size, is 2 power n, and the logical space you need for the process is 2 power m, Then you take your address in binary, of course. The first m minus n bits indicate the page. The remaining one indicate the offset. So you can translate the binary address into page and offset just like this, okay? Let's look at the example. So here we have a process, it's 4 pages, each page has 4 addresses, we have the page table, and we have the physical memory. The page size is 2 power 2, okay? So n is equal to 2. The logical space is 2 power 4, so m is equal to 4. Because as you can see, we need, in this case, 4 pages for a total of 16 addresses to maintain the process in memory. So what is the physical address of logical address? 7. Well, you take 7, you put it in binary, and then you take the prefix, which is in this case the first 2 bits, to compute what is the page, and the last bits to compute what is the offset. This is saying that is page 1, offset 3. Let's see. Page 1, you go in the page table, and it says that it's the 6th frame. So you do 6 times 4, because the size of each frame is 4. You add 3, which is the offset. So the physical address is 27. And if you go to 27, you will find here H, which is what you want for address 7, okay? Try the example out yourself. Now, I cannot cover it too much in detail. It would take a lot of time, but if you try yourself with a piece of paper, you will see that it's not that complicated. Now, as always, we have trade-offs. The good thing with paging is that there is no external fragmentation. If you need to load n frames, and you have, n pages, and you have n free frames, then it's okay. You can place each page in a frame, even if these frames are not contiguous, independently of where they are. On the other end, you end up having internal fragmentation, okay? You need to use at least 1 frame for a page, for each page of the process. And it might be that the process does not really require a full page, or maybe it requires 3 point something pages. So on average, half of the last page you need for the process might be wasted, okay? Of course, if you want to minimize internal fragmentation, you can go for smaller pages, but you will have more overhead. You will have a larger table to maintain. You can also go for larger pages, so you have less overhead, the page table is smaller, it takes less space, but of course then you end up with more fragmentation.